All right, methane. So our first approach is going to be valence bond theory. And you're going to say, so what? Isn't that basically what we did with hydrogen? Valence bond theory comes from, among others, the chemist Linus Pauling. And he was dealing with a problem of how you get the geometry of methane, which is tetrahedral. Valence shell electron pair repulsion tells you it has to be tetrahedral, right? But the problem is that if we think about the orbitals that carbon comes with, hydrogen, of course, comes with a 1s orbital, and we have 4 of those because we have 4 hydrogens. But carbon comes with a 2s orbital that's just a sphere. It's a slightly larger sphere than the 1s orbital. And actually, if you really want to know, which you don't, the 2s orbital is like an egg. It has a yolk inside that is opposite in wave function sign to the outside surface. So the 2s orbital has 1 node. And then there are 3 other orbitals, the 2px, the 2py, and the 2pz. And let's adopt a coordinate system where this is x, this is y, this is z. I don't know, nor do I care whether it's right or left-handed, and if there's a way that you prefer and I didn't do it, I am sorry, but not that sorry. Not sorry enough to do anything about it. That's repentance, right? All right, so the, just kidding. Anyway, the y orbital would be coming out towards you. The x-axis is in the plane of the page. The 2pz orbital is aligned with the z-axis. I can't remember what colors we chose. I'm using colors here to represent wave function sign. So what we mean here is perhaps the wave function is greater than 0 over here, and the wave function is less than 0 over here. And we mean just mathematical sign of the wave function. Now you could ask, why don't I put a plus here and a minus there? And that is because we want to use pluses and minuses to refer to charge, not to the sign of the wave function. The mathematical sign of the wave function or its amplitude really has no physical meaning. We just use it as a way to pay attention to when destructive interference occurs, and in particular, where there are locations that are called nodes. So for the 2px orbital, there is a node. It's actually a nodal plane. I'm not sure how to draw this, so we're just looking at the x orbital on its side. There is a node here, and the node indicates a place where the wave function goes to 0. All right? So if something goes to 0 on one side, it's got to be positive, and the other side, it's got to be negative if it's continuous, right? So I'm going to use color as we draw orbitals to indicate wave function sign. It's going to be useful to us. It's fine if it doesn't seem useful now. Any questions you want to ask about that? Okay. For the 2s orbital, there is a node, and it is this sphere, and it's a sphere that surrounds, or a spherical surface that surrounds the nucleus and is a border between an area where the wave function is positive versus where it's negative, and it is a location where wave function equals 0. Notice, by the way, that the 1s orbital has 0 nodes, whereas all of the orbitals from the second row of the periodic table have 1 node. All right? Okay, so Pauling looked at the tetrahedral structure of methane and then considered the fact that he could envision easily making each of these bonds from an atomic orbital on hydrogen with an atomic orbital on carbon, because of course you could have this bond involve overlap of a 1s orbital from hydrogen with some atomic orbital on carbon. The problem is that the angles don't work out, right? The 2s orbital, the bond angles don't work out. The 2s orbital is basically a sphere, so if we put it here, maybe we could make a bond in the same way that we made with hydrogen, right? Maybe they could overlap in phase. But what about, and maybe, all right, so we could envision making this bond here, and we could even envision making one of the other carbon-hydrogen bonds, perhaps by having a 1s orbital on hydrogen overlap with one of the p orbitals on carbon, right? The problem is that the other hydrogens can't line up with the p orbitals, right? Because the p orbitals are 90 degrees away from each other, whereas the bond angles in methane have to be 109. Does that make sense? We can't get those p orbitals in the right direction. And so to solve that problem, Pauling did something pretty creative, and that was to say, okay, what if I mathematically mix these together? What if I mathematically add the 2p, the 2s, the 2px, the 2py, and the 2pz together? Mix them together mathematically and see what comes out. Now, the mathematical process of doing this is beyond the scope of the class. It probably involves matrices, and goodness knows that we don't want to do that. But what you get when you mix these together is you get 4 new hybrid orbitals. You've heard about hybridization, right? It's an old concept. These hybridized orbitals they look like p orbitals, but they're distorted because they also include s characters. So they have this sort of balloon shape with a small side and a large side of opposite electron density. This is an sp3 hybridized orbital. And there are 4 of these, and it turns out that they are each 109 degrees away from each other. So there are 4 unique sp3 orbitals, and if I tried to draw them all in the same sort of shape, we'd get something like this. We're going to ignore the small lobes for a minute, but the effect of Pauling's hybridization is simply to orient the large lobe of each hybrid orbital along the axis between carbon and each hydrogen. So they now point in the right direction. I don't think I explained that particularly well. Questions? Yeah. Oh, no. The confirmation. Okay, I got an A. Okay, that's good. That's good. I'll take that. And we're still rolling. So far, so good. Therefore, Pauling envisioned that each bond in methane would come from an sp orbital on carbon with a 1s orbital on hydrogen. So he envisioned adding the sp3 orbital on carbon with a 1s orbital on hydrogen. And when you did that, you would get a bonding orbital that would basically envelop the space between carbon and hydrogen and envelop the hydrogen nucleus entirely. It would have a node at the carbon nucleus, because all of the p orbitals have nodes at carbon nucleus. But you would get constructive overlap, constructive interference between those 2 atomic orbitals, and a bond would consist of 2 electrons in that bond that you get from bringing an electron from the 1s orbital of hydrogen and an electron from the sp3 orbital of carbon. They called this kind of bond a sigma bond. And sigma, it's called sigma because I don't know why, actually. the sigma bonds are what we call cylindrically symmetrical, which means that if you rotate one partner in a sigma bond relative to the other, you don't change the ability of the orbitals to overlap. So conceptually, do you see how if I brought these two together and then I took the carbon and spun it around, there's no change in the orbital, right? Because it's cylindrically symmetrical about this axis between the two atoms. So we call that, because it's cylindrically symmetrical, we call it a sigma bond. And electrons in that sigma bond tend to be in between the two nuclei. And frankly, so far this picture is not that different from what we did with hydrogen in the first part of the class. This is a cylindrically symmetric orbital where the electrons would spend most of their time between the two nuclei, where they would have lower potential energy and lower kinetic energy. So same basic concept. This would lead you to the conclusion, if you could measure the orbitals in this would lead you to the conclusion that if you could measure the orbitals, energy of the orbitals in methane, that you would have 4 identical sigma bonding orbitals, each of them from one of the sp3 orbitals on carbon with a 1s orbital on hydrogen, to have 4 equal in energy sigma bonds. And that sort of makes sense because we draw the Lewis structure of methane and all the electrons are in the same kind of bond. 4 identical bonds, got to have 4 identical orbitals, right? Okay, questions about that? Now, sometimes experimentation makes us have to revise what we thought we knew and what makes sense. And it turns out, in reality, even though we expect this, we actually observe that in methane there are 3 identical orbitals, and then one of them is lower in energy. Ick. How are we going to explain that? Does it even matter? The good news is it's not going to matter for this course. But I'm going to show you how you deal with this problem so you can appreciate the simplicity of what we're going to fall back to. So I'm going to pull back the curtain a little bit, and you're going to see the horror that awaits beyond, and then you're going to be content when we get back to the stuff that we'll deal with. So it turns out that you can approach methane. Valence bond theory, the key piece of valence bond theory is that a bond is 2 electrons shared between 2 atoms, period. That's what a bond is. Molecular orbital theory takes a different approach. And in molecular orbital theory, we generate electron pairs are in an orbital that is a molecular orbital, sorry, it no longer works, and molecular orbital, whatever, that spans the whole molecule. And you generate the molecular orbital, you get it from combinations of the available atomic orbitals. So if we think about what's available, we have 4 of the 1s orbitals from the hydrogens. And then we have a 2s orbital, 2px, 2py, 2pz, okay, from carbon. So let's imagine making a molecular orbital that spans the whole molecule. I'm going to draw this conceptually. I'm going to keep our lines so that we can see where the hydrogens are. We could imagine conceptually combining each of the 1s orbitals on the hydrogens with a 2s orbital on carbon. And if they overlapped with the same wave function sign, we can imagine a molecular orbital that would actually look something like this. You'd have a carbon in the middle, a hydrogen here, a hydrogen there, a hydrogen here, a hydrogen there, and then the overall molecular orbital would look something like this. And a single electron pair, oh shoot, I needed a slightly bigger font there. Tired of coloring. There we go. Much easier. A single electron pair would then occupy all of that space. And this we could represent this as 1s plus 1s plus 1s plus 1s plus 2s. We get one molecular orbital out. Notice that we are losing entirely in molecular orbital theory the concept of a bond. Which bond does that pair of electrons represent? And the MO theory person says, what is this bond of which you speak? Right? Which, of course, they know what bond you speak. It's sort of like coming home from the mission and saying, what is the word in English again? Anyway, sorry. If you've done that, I'm sympathetic. I apologize. I'm not trying to make fun. Okay. Except there was this, sorry, I easily go off on tangents. Years ago when I was a teenager, there was this guy that came home from his mission in South America somewhere, I think it was Peru, and he gave his entire welcome home address. This was back when we had such things, but you know, a returning missionary still speak at sacrament meeting. Anyway, he gave his whole thing in, I think, what was affected and heavily accented English, which I, in retrospect, found kind of offensive, right? I don't know. So, I don't know what that has to do with anything. It's neither here nor there. But I will occasionally go off on tangents. I apologize for that. Now, that's one of the orbitals from methane. There's a program I have on my iPad called Spartan, where you can, oh, looks like my children have been shopping. Okay. Where you can draw molecules, and then it will show you what the orbitals look like if they're available. And that's just going really well, isn't it? All right, and 3D, that's methane. I'm going to download the orbitals and show them to you. Remember how I told you one was lower in energy? That's what it looks like. So see the similarity there to what we drew here, right? 2 electrons delocalized across the entire molecule. And we no longer care which bond they go with because they don't go with a bond. They're just in an orbital. Okay, what about the 2p orbitals? Well, it turns out if we choose our x, y, and z axes appropriately, and I'm trying to figure out how to do this in a way that makes sense. Let me go back to the Spartan program. If we choose our x, y, and z axes carefully enough, let's see, will it let me twist? No. So I'm going to try to align this molecule so that the carbon-hydrogen bonds, the one that's going up and the one that's going to your left, are in the plane of the page, and then one of them's coming forward and one of them's coming back. Imagine, ooh, I get to get out my laser pointer, which I hardly ever use anymore. Nope, not that. Here we go. Imagine putting a p orbital aligned sort of from here to here so that one lobe could overlap with the 2 hydrogens here and the other lobe could overlap with those 2 hydrogens there. I'm going to draw that and then show it for you in the Spartan program. Let's take 2 of the 1s orbitals on hydrogen here. Oops. And let's have it overlap with, and let's take the 2 1s orbitals on hydrogen there. Let's have them be opposite in wave function sign. And then let's take one of the p orbitals and align it along this axis such that it can overlap with the same wave function sign with the orange hydrogens and with the pink hydrogens. What you would see overall if you added these together would be an orbital that has sort of a kidney shape here. And then another one also with a kidney shape, but in another orientation, which is pretty hard for me to draw. So I'll just, if we were to draw this without the lines to guide our eyes, what would we see? Something like this. And then that's hard to do, maybe. And there would be 2 electrons in it. Those 2 electrons, by the way, are not hopping back and forth between those 2 areas. They simultaneously occupy all of it. In the same way that in our original lecture, the wave is not hopping back and forth between positive or negative, it just is, all of those things, okay? So the electron is a wave. It goes to 0 at the carbon nucleus, but it covers some of the space between the carbon and the hydrogen, and it allows you to be closer to the nucleus and for the slope of the wave function to change less dramatically. So that's lower kinetic energy and lower potential energy. Let me show you, since this is sort of difficult to envision, let me show you what it looks like here in our Spartan program. Yeah, there we go. So in red are the 2 hydrogens overlapping with the lobe of the p orbital. These are the ones that are in the plane of the page. And then this in blue is the 2, what were our 2 pink hydrogens. One's coming out at you, one's going back into the page, and they're overlapping with the other lobe of the p orbital. So you can see you've sort of got these orthogonal hot dog buns. I mean, it's a terrible way to eat a hot dog, but it works with the system that we're looking at, okay? And you can do that 2 other times using the other 2 p orbitals, and that's where each of these comes from, okay? We're not going to do that 2 other times. We're just going to remember that you've got 2 other combinations. And let's just, for fun, call this the 1s plus 1s plus 2px minus 1s minus 1s combination, where there's a change in phase here. Also note that this orbital with a single node between hydrogens and carbon, or at the carbon nucleus, is higher in energy than this orbital that doesn't have a node at carbon. That's because the wave function slope changes more slowly here, and kinetic energy is therefore lower. Here you can tell the wave function changes, slope changes more quickly because it has to go through 0. Another way of recognizing that one's higher in energy than the other is to recognize this one has a node at carbon, whereas this one doesn't. All right, so that picture gives us a more realistic view of what, of the actual observed electron energies in methane are. However, as molecules get bigger, it's tougher to keep track of. And in particular, one of the things I didn't mention, but we talked about in hydrogen, was that if you you have to get the same number of molecular orbitals out as you put together. So I've shown you 2 of 8 possible options, which I realize is horrific. Some of the other options look like this, and that's sort of just bizarre. And so actually this one's not that bad. This one is what you would get if the 2s orbital in the middle was a different mathematical sign than the 1s orbitals out on the hydrogens. Right, like if we had this. That's sort of this combination. So in molecular orbital theory, we do pay attention to the empty orbitals that can form as well, and those often have important consequences, which we'll deal with soon. However, it gets to be a little much. So what we're going to do for the most part is to take a hybrid approach between valence bond theory and molecular orbital theory. Remember, in valence bond theory, we thought a bond is 2 electrons shared between 2 atoms, and conceptually we made that by overlapping 2 atomic orbitals. But we neglected completely the concept of empty orbitals. We can't do that because the concept of empty orbitals is going to be useful to us as we learn how to predict organic reactions. So our valence bond theory and molecular orbital theory hybrid is going to involve, first, the idea that sigma bonds are localized between 2 atoms, but we're going to remember the sigma star antibonding orbitals, that we're going to remember that they exist. So our valence bond theory picture is going to give us the same origin of the sigma bond between carbon and hydrogen, that is, overlap of a 1s orbital on hydrogen with an sp3 orbital on carbon. And in methane, we're going to say that that gives us 4 equal in energy sigma bonding orbitals. And those are all lower in energy relative to our sort of 0 break-even point. But that also present, higher in energy, are these empty, unfilled antibonding orbitals. Okay? And that's going to give us a lot of what we need to know. Now, what does the antibonding orbital for a sigma bond look like? Well, just as you get the sigma bond in concept by bringing a 1s orbital together with an sp3 orbital together with the lobes overlapping in phase, you simply slide this one over and you get something that looks like what we've drawn there. That is a sigma bond. That's the plus combination. We're going to get the antibonding orbital from the minus combination. So what would that look like? Bear with me for a second. The minus combination would be the same as the plus combination if I change the wave function sign. Okay, so now conceptually, let's imagine bringing these 2 together. As they overlap, same thing we saw with hydrogen, they're going to cancel out in the middle. All right, so the antibonding orbital is going to look like this. Here's the carbon hydrogen bond. There's going to be a node in the middle. Most of the electron density is going to be out away from the space between the 2 nuclei because it's been canceled out in the space between the 2 nuclei. So actually there will be a small lobe on carbon because it's been canceled out, and the larger lobe will be pointing back away from the carbon-hydrogen bond. This is our sigma star. It's a carbon-hydrogen sigma star. This is a carbon-hydrogen sigma bond. Okay? There is a node in the middle where the wave function goes to 0. You can see that if I put electrons in this orbital, they would tend to pull the two nuclei apart. And you can also see that electrons in this orbital would be farther away from the nucleus, and you change wave function signs twice instead of once. That means your slope is changing faster, which means your kinetic energy is higher. All right, so the sigma stars are all up here, the sigma bonding orbitals are all there. So our hybrid approach is gonna acknowledge, we're gonna say, okay, fine, it's easy, let's just think about bonds as being two electrons shared between two atoms, but don't forget the antibonding orbitals, because they're gonna have an important role later on. Okay? Questions? All right. There's one other, I'll just make a note that we're going to need another couple of concepts to help us get to good conclusions using our valence bond theory approach. And that is, we're going to need to deal with resonance and something called hyperconjugation. Let's deal with resonance first, and we're not going to spend a lot of time on resonance because I believe you've dealt with this in a lot of detail in previous classes. Resonance, in terms of valence bond theory, is when you can draw two or more legitimate Lewis structures for a molecule, and then you conclude that none of them represent the real structure of the molecule, but that the real structure is a hybrid of all of them. Is that sounding vaguely familiar? Yeah. So an example of this would be the following anion. And we can label carbons 1, 2, and 3. But we would use this double-headed arrow to indicate that we can draw another resonance structure in which the pi bond is between 2 and 3, and the negative charge is on carbon 1. This drawing presupposes that you know about resonance and you also know how to assign formal charge. Those concepts are critically important for this class. They're also pretty easy to learn, so I'm going to let you do that on your own. If you struggle with that, there's a lot of problems in the optional but useful introductory study guide that will be on the content page of Learning Suite as soon as the system lets me press go and publish the course. So ideally, you need to be able to look at this and say, I know exactly what you mean by this. I know that you mean that there's a lone pair of electrons on this carbon. That carbon normally comes with 4 valence electrons. It currently owns 5, so it has a negative charge. Expect you to be able to do that. And if you can't, just review it. It's not that bad. And then resonance, being able to get from here to here. Understanding that resonance does not mean that the lone pair is hopping between carbon 2 and 3. Which one am I on? Oh, now I'm over here. Now I'm over there. No, it simultaneously occupies both positions. And in fact, sometimes people will draw, and I don't like to do this because we sort of lose track of the electrons, but sometimes people will draw a hybrid structure that indicates that we've got partial double bond character between 1 and 2 and between 2 and 3, and then they'll put this Greek letter delta, lowercase delta on 1 and delta minus on 3 to indicate that this single negative charge is shared between those two carbons. All right? Now, the valence bond theory approach without resonance would lead you to an incorrect conclusion. If you thought that if you didn't have resonance, you would look at these two and you would say, oh, I have a double bond between 1 and 2. And actually, double bonds I know are shorter than single bonds, so the space between 1 and 2, that distance has to be smaller than the distance between 2 and 3. And over here, the negative charge is on carbon 3, whereas 1 and 2, 1 isn't negatively charged. And then you have similar conclusions, but with different atoms over here. In reality, the bond distances between 1 and 2 and 3 are identical. and there is the same amount of negative charge on carbon 1 as there is on carbon 3. So without resonance, valence bond theory is going to get you to the wrong place. So you've got to remember resonance. But it will, and if you can remember that, probably you're fine without delving any deeper into molecular orbitals. Though for a particular chapter in the class that's coming later on in the semester, knowing some things about molecular orbitals and resonance will be really useful. So to introduce this idea, I want you to look at these two resonance structures. And I want you to notice that in either resonance structure and in the hybrid structure that I've drawn here that represents both of them, notice that the sigma bonds are not changing. They stay the same. Resonance is involving the pi bond and the lone pair. All right. I'm not telling you what the rules of resonance are. This introductory study guide goes through that. It's really important, but I want you to learn that or review that on your own. But when we have a situation where there's resonance, we can use our valence bond theory approach for the sigma bonds because those aren't changing at all. But when resonance occurs, we'll want to use a molecular orbital theory approach to deal with the pi bonds and the lone pairs that are changing from one resonance structure to the other. Okay, so let's talk about the atoms in these resonance structures. What is the hybridization of, in the resonance structure on the left, what is the hybridization of carbon 1? Sp2, okay. If that's a little bit hard to remember for you, remember the way we talk about hybridization. First, you recognize that the carbon is surrounded by only 3 things. Therefore, it must be trigonal planar. The way you get trigonal planar geometry is from Sp2 hybridization. An Sp2 hybridized atom has 3 Sp2 orbitals, which for our purposes look exactly like Sp3 orbitals, only they're a little more stubby, and they are oriented at 120 degrees with respect to each other. Left over is an unhybridized p orbital. Okay? If carbon 1 is Sp2 hybridized, tell me what orbital on carbon contributes to this sigma bond between carbon and hydrogen. Where do we get the sigma bond between carbon and hydrogen? Which of the orbitals on carbon, which of the atomic orbitals on carbon contribute to that bond? Okay, on an Sp2 hybridized carbon, you've got 3 of the Sp2 orbitals. So yeah, we get this sigma bond from overlap of an Sp2 orbital on carbon with a 1s orbital on hydrogen, right? Same thing here with this carbon-hydrogen bond. For the sigma bond between 2 carbons, we can get that by overlap of 2 Sp2 orbitals, just end on end. I'm not drawing that, though the study guide will take you through that a little bit more systematically. Where do I get the pi bond from? Okay, the pi bond and the sigma bond together make a double bond. Good. Double bond equals a sigma bond and a pi bond between the same atoms. Do you remember where you get the pi bond from? Okay, let's go ahead.
Is it overlapping p orbitals?
Overlapping p orbitals, right. So let's remember that each of these carbon-hydrogen bonds are in the plane of the page. The p orbital that we have left over on that carbon 1 would be coming out of the page towards us, and then going back into the page away from us. We're looking at this molecule from the top down. And we could use a similar approach to conclude that there is another unhybridized p orbital on carbon 2 with, again, a lobe oriented towards us and then one oriented away from us. Okay? We're going to get the pi bond from side-by-side overlap of those p orbitals. So if we take the 2pz orbital and add it to the other 2pz orbital, we get what's called side-to-side overlap. And if we do this with the in-phase constructive interference combination, you get side-by-side overlap. If here is carbon 1 and here is carbon 2, the pi bond really looks like a lobe of electron density above the plane that contains atoms 1 and 2, and then a lobe of electron density below the plane that contains those atoms. So this is what a pi bonding orbital looks like. Does that look somewhat familiar-ish? Maybe? Okay. So we're going to need to stop there for today. I want you to work on the study guide till you get to the point where you're comfortable not only with the pi bond, but also with the anti-bonding minus combination, which we're going to call the pi star. Okay? A lot of stuff to do. Got your work cut out for you. I will see you on Friday.